Now let's look at another application of trigonometry. Um, we will use the trigonometry in writing the complex numbers in polar form. So we will see trigonometric form of complex numbers and product and quotient of complex numbers in trigonometric form. So this here is about the fractals, and this fractal set is obtained by complex numbers. So this is an interesting topic. So now we will look at the complex numbers. Now the first thing is I want to tell you is x, here the complex number, we write them as a plus bi. Now we want to put this in the complex plane. In complex plane, the complex plane is Cartesian coordinate plane. But the x-axis, we will use the x-axis for the real part of the complex number, and we will use the y-axis for the imaginary part. So when we say like 2 plus 3i, it means this 2 plus 3i. So the imaginary part is 3, and the real part is 2. So this is the situation. Now I will not use this x and y here, but I will just say here real part. This is the real part, and this is the imaginary axis. So the real axis and the imaginary axis, I will say this is a complex plane. Now I will say this is the complex number here is x plus yi. So this point is telling you the place of x plus y, I, in the complex plane. So here, this one is called this length here. So we will call this z equal to x plus yi now. Okay, let's say this is z is equal to x plus yi. And now this, okay, this is the complex number x plus yi. And it's by Pythagorean, this length is square root of x squared plus y squared. So we will call this one the absolute value of z, or the modulus of z. So the modulus of x plus z equal to x plus yi is indeed, we show it this way, which is equal to square root of x squared plus y squared. You know, in the vectors, if in the vectors it was the magnitude, it's the same thing here. The magnitude, you know, in different terms, in different concepts, we have different names for the same thing. For the magnitude of the vector here, vector xy is, you know, is square root of x squared plus y squared. So here we were saying this is the magnitude of vector in the vectors, but here we will say the modulus of z equal to x plus yi. So it's, yeah, mathematically they're the same, but here when I say x plus yi, the complex numbers, I mean x plus yi. Now we are dealing with the complex numbers, not the vectors. But geometrically, you can think the same way. Now, in terms of lengths, let's say. Now, the other thing here is this is a complex plane now, and when you put the complex number on the plane, when you locate it, for example, you put x plus y, okay, let's put z equal to -3 plus 4i. So where is it? -3 plus 4i is -3 is here, and 4i is here. So the imaginary axis, it's the real part. So it will be -3, 4 pi, 3 plus 4 pi will be this. 3 plus 4 pi, 4i, sorry, not pi. And here, if you draw this modulus here, I mean, not the modulus, but if you draw this line here up to -3 plus 4i, then there will be this angle here. This theta, this angle, is, we say, is the argument. We call it argument now, the angle. We don't say the angle, but the argument of -3 plus 4i. So if it is xy here, so I will generalize it now. So I will give it in terms of x and y. It's almost same thing, x plus yi. So we say theta is the argument of x plus yi. This time it was the direction angle and the vectors, but now it's the argument of a complex number. So as we know, this tangent theta will have this property y over x, and this is coming from, remember this, if this is x and this is y, and this is theta. Now you remember this, I guess tangent theta is equal to y over x, and you can say also the cosine theta and sine theta. You know the formulas, we have seen it at the in the section 1.2. Now, if I want to repeat again, we are doing the same thing as in the vectors, but we give different names. So this here, again, x plus yi. This is theta, argument. But in the vectors, we were doing it. xy. And this theta was, okay, in the vectors, it's a vector here. In the previous section, it was like that. And theta was the direction of angle. This was the modulus here. The modulus, the length here, modulus of z. Okay, let's call this one also u, the vector u. And the length here is the norm of u is called the magnitude of u. So the length of u or the magnitude of u. Usually they are all same, but except one of them is representing the vectors and the other is representing the complex numbers. And the rest of the things are almost same. So here there was a Java applet, and we were showing how z changes here with respect to the angle, but anyway, it doesn't work. Let's skip this one. Now, again, the same thing here. How can you find, if you have x plus y complex number, how can you find the argument? It's just the same as in vectors. Just find tangent inverse the absolute value of y over x. Like here, x and y is what here? Again, it's x and y is here. This x, this is y, and now we say it's not a vector, but we say it's corresponding to a complex number here. Like we were doing it with the xy, before, and the vectors. But now we don't do the vectors. We just say it is complex number, x plus yi. So same thing, it's theta is in here, and this alpha should be in here, the reference angle. Then we can find theta in the second quadrant, 180 minus alpha. It's the same thing. Now, but here, again, yeah, we had this issue here, v sine theta. Here, this r. So if it is a complex number, x plus yi, then we can write this one in polar form as this r cosine theta and I sine theta, which comes from, again, this one here. This is modulus. We call it r. Okay. This is theta. This is x. What is x? So x, indeed, x over r will be cosine theta. So we can say x is equal to r cosine theta. And in the same way, y will be r sine theta in the same way, because it's y over r will be sine theta. So if you multiply these two, but this, so instead of x and y, we can write r cosine theta and r sine theta. And of course, since this is a complex number here, we write x plus yi. So zx equal to x plus yi can be written as r cosine theta plus I r sine theta. And instead of writing this way, we just say r cosine theta plus I sine theta. And this one is called CIS. Okay, r CIS theta. So when we say this one, it means cosine theta plus I sine theta. And this theta is the angle coming from the previous information. And here, this theta is called the argument of complex number. This theta is called the argument, by the way. So if okay, remember this? Remember. Theta, direction of angle for x, y. But theta now, it's argument of x plus yi. We find it the same thing. But in complex numbers, the argument of x plus y, and it's here the direction of xy, the vector xy. So as you know, as you see, this x squared plus y squared, magnitude of the vector xy. And but here, x squared plus y squared, we say the modulus of x plus yi. So they're all same. They're all same, but with different names. Under the different names, mathematically they mean the same thing. Okay, how to convert? Okay, now sometimes we are given this way. Here sometimes we will give given this way, then we ask what is xy here. So rectangular form means this one here, xy, x plus yi. Rectangular form. Trigonometric form is r cis theta. So sometimes we do this, sometimes we go backward. Now let's see this one. What is this equal to? You basically just write 3 cosine 60, write this one clearly, and sine 60, and put the numbers here and numbers here, and then you multiply them, you get these. Okay, now you have to be careful about, finding cosine 5 pi over 6 and 5 pi over 6 here. And this is kind of 150 degrees, and you have to use the reference angle. So I leave it to you. Please verify them, check them. And it's pi here, 180 degrees, and you know how to find 180 degrees. This is my method here. I'm all the time using the unit circle. It's cosine 180, comma sine 180 is here. So this is like minus 1, 0. So cosine 100 will be equal to minus 1. This will be 0, and we will get minus 5. Now let's do the reverse. So it's rectangular coordinates. Now we want to get to r cosine theta, not cis theta. Okay. Now how can you find? First, you will find r. R means here like the square root of x squared plus y squared. And then we will find the others. But how? Okay. So if you match them, this is the idea. Okay. X. What is r? R is x squared plus y squared. And then this turns out to be cosine theta will be, x squared of x squared plus y squared. These indeed cosine theta and sine theta will be indeed, you remember this, your x and y, this theta. So you say this cosine theta is equal to x over square root of x squared plus y squared. Sine theta is equal to y over square root of x squared plus y squared. We can use the same formula. So we did that for the terminal side. You can do the same thing for x plus yi. There's nothing wrong here. We are doing the same thing under different notations. Let's see how it is done. The slide. Let's follow the slide. So it says, first I find the r. Okay. Now, think of this. R. So you find, okay, put x and y in the Cartesian system. It's 2. And minus 2 is where? It's minus 2. We have this point, and now we have this angle here. This will be our theta, and z will be z means here like 2 plus minus 2i, so it will be z is 2 minus 2i, so it's this one. Now we are trying to find this theta, and now I need the reference angle. So what's the reference angle? Reference angle will be tangent inverse minus 2 over 2. So this is y, this is x. So minus 2 over 2. Its absolute value, it will be 1. So we get 45. So 45 is here. And now the rest is easy. Theta will be in the fourth quadrant, and it will be 315. Now again, the same thing happens in here. It's when you can say it's 1 square root 3 here. So what's the ref angle? Ref angle here is in the first quadrant. In the first quadrant, the reference angle will be equal to the angle itself, theta. So reference angle will be what then? So how do you find the reference angle? You just look at ref angle alpha is equal to tangent inverse the absolute value of y over x. What is y over x? Y is square root 3 divided by 1. So it has to be 60 degrees. So alpha has to be 60 degrees because tangent 60 is square root 3. Now so the reference angle is 60, but the point here, the complex number here is again in the first quadrant. So it has to be, theta has to be 60 degrees. So in this case, what we write here is this has to be 2 times CIS 60. So as you see, now I explained how to get 60 and 60 here. And r is of course the square. I mean, it's 1 squared plus square root 3 squared, and take the square root. Like 2, you will put 2 here, and then CIS, and then our theta. Sorry, not the reference angle, but the theta. Now u equal to I, so you can find r here. R will be equal to 1 because this means 0 plus, okay, 1i. So your x is 0 and y is 1. Okay. Now x is 0, y is 1, and u is on the positive axis. Okay. So where is it? It's 1, 0 is here. So 1, 0. No, this is 0, 1. 0, 1i. So it has to be here. Now which angle is it? It's obviously 90 degrees. So you can say, hey, it will be just 1 times CIS 90. So this is how we find it. So you should be able to do both, like from rectangular to trigonometric form and trigonometric form to rectangular. You should be able to do them. And so let's look at this exercise here. Okay, you can follow the steps here. I just want to tell you this r, when you calculate it, will be 8. So it's like So when you do this, you will get r squared will be this, and r is equal to 8. Now the other thing we have to is like what's the reference angle here? Alpha, this is x and this is y. That's tangent inverse of the absolute value of this minus 4 over tangent inverse is 1 square root 3, and then this will be 30 degrees. And 30 degrees is this. Now it's in the fourth quadrant. This minus 4, sorry, this is not in the fourth quadrant, it's in the third quadrant. So minus square root 3 and minus 4i is here. So it's in the third quadrant, so quadrant 3. So theta is here. Reference angle alpha 30 degrees. So alpha. So what is this angle? Obviously theta should be 180 plus 30 degrees has to be 210. So what is this then? This will be R8 times CIS 210. So we are done. Okay, here you might need to use a calculator for it. R is equal to 5. I mean, no calculator needed for this, but I'm saying for this one. So this has to be, if you do it, it's almost like 53 degrees. So then this one is in quadrant where? It's in quadrant, is it? It's here, Q4, Z here, 3 minus 4i. Okay, now in the complex system, complex system, we always y values are I. Now quadrant 4 and this reference angle is 53, so you say this is 53. So what is the angle here? The angle has to be 360 minus 53. This will be 307. So it will be just 5r. And then this one here, theta, CIS, theta 307. So it's approximately, because I'm taking this one approximately. Okay, this is the last subsection we will see, and we will see an interesting property of complex numbers. So if two complex numbers are written in trigonometric form, then interestingly, if we multiply these two numbers, these complex numbers, then it will be the product of the modula or modulus, or 1 times R2 times CIS theta 1 plus theta 2. So this is interesting. R1 times R2 is nothing is interesting in here, but the interesting thing is this: CIS theta 1 times CIS theta 2 is equal to CIS theta 1 plus theta 2. Can you see it? Like, okay, I will show you a method. We will not show you how to show it. I will not go in detail. I will just give you the beginning of this. So you do multiplication and doing this, and you will end up with, interestingly, you will have some, formulas for cosine theta 1 and theta 2. You will get something here from this multiplication. It will correspond to this. You can check this one. It's cosine, sine, with minus. And then it will be I sine theta 1, theta 2. So after doing this, you will see that, okay, by using the identities, it is clear. And Okay, we will not show you in detail like they are same, but you can find it by yourself. Like if you want to see, you can do the calculation and you can match them directly. Now another property here, what we have seen is this z1 times z2, which is equal to this, and by default, by setting of them, now it will be equal to this. And now if we divide them, interestingly, this is interesting, CIS theta 1 divided by CIS theta 2 is equal to CIS theta 1 minus theta 2 is R1, R2 is R1 divided by R2 is still same, but this is interesting. So CIS, which means like cosine theta 1 plus I sine theta 1 divided by sine theta 2 plus I sine theta 2 is indeed interestingly, this is cosine theta 1 minus theta 2 plus I sine theta 1 plus minus theta 2. So, okay, you can calculate this one by, multiplying with its, conjugate. Do the same thing here and here. And after this, you have to see this one. You will do lots of work here, multiplication, and then the identities, use them, and at the end you will get this. Now, okay, so for you, the important thing is you have to know the formulas. That's it. Okay, you have to know the formulas. That's it. Now, let Z1 is this, and let Z2 is this, and let's perform the operations between these complex numbers given in trigonometric form. Z1 times Z2, and what's the formula for it? It's basically Z1 times Z2. You multiply these two, R1 times R2, and you say CIS theta 1 plus theta 2. And this is how we do it, by using directly the rule here. And what is this? 300. 300 means, okay, what is cosine 300? It's we know the reference is 60 and cosine is positive there in the fourth quadrant. And when it comes to the 300, it will be minus sine 60. We will put them here and we will see it. Now we will write them in a rectangular form. So we just, because in the question it says rectangular form, so we write them in rectangular form. And we can use the other formula to find this one. So basically it's 12 over 2. So you divide the modulus, and then theta 1 minus theta 2. And it's 150. So we know how to use the reference angle here. And it will be this one in rectangular form. Now let's look at the try and check. It looks a little ugly here. What I can say here is this one is directly 48 times CIS. When you add them, it will be 270 degrees. And cosine is, it's 0 here, and the sine is -1. It has to be -48i. Please check. It has to be -48i. And Z1 times Z2 divided by this, it will be 32 CIS. 70 plus 160, it will be 230. Divided by Z3, 6 times CIS, 110. So it will be 32 over 6 times CIS. This thing will be equal to 120. And you will find the values and you will multiply with this. So you can find the solution by yourself. Now, one other interesting property here is If a complex number is written in this form, then its nth power is equal to the nth power of r times CIS and theta. So this is a nice formula, and it's coming from the previous one, because z is r sine r CIS theta. Now z times z is what? So this 2 will give you r squared, CIS theta times CIS theta. From the previous property, it's CIS theta plus theta. So it gives you r squared times CIS 2 theta. So it will be z squared. So if you do it more, you'll get this formula here. Let's perform these operations here. Z1 to the 6th, so Z1 is here, and if you want to use the 6th, find the 6th power, and you have to use the formula here, because this is given in terms of trigonometric form. So it take the 6th power of this, it's okay, 27, you can check. And now 6 CIS, for CIS, 6 will go inside here. So then 150, and I'm using this property here. And then you can calculate these, and you will get this one in rectangular form. So pay attention to here. If it says rectangular form, you have to do it this way. Now let's do the other one, 5th power, so it has to be, okay, 5 to the 5th, but for CIS we can take it inside, so it will be 300, and use the reference angle here, and plus, and all STC, and then you will get this one and the rectangle, so it will be this. And let's do this one, 5th. Okay, it will be 5th one, so we will multiply this with 5, you see. Five times 60, and we do the same thing for the other one, Z1, 6. I take the 6th power, and we already found them, by the way. It's here and here. See, I mean here. Put them here, and now for the division in CIS, we have this formula here: 300 minus 150, and this will be equal to, in terms of the reference angle, it will be negative cosine 30 and sine 30. And when we put them here, substitute, we will get this one. Now, this is the end of the lecture. Thanks for listening.